All right, everybody, welcome into this special edition of your favorite class, obviously. I'm out on Wednesday, the 25th, so today we're going to be doing a little bit of a special lecture where I have to record this beforehand and then present it to you. Jury duty, good times. I'll be in jury duty on Wednesday, Thursday. Very exciting. So I'll go for maybe about 50 minutes. It's Tuesday afternoon right now at 12:48, so 50 minutes would be 12:38. So try to do about 50 minutes of lecture here. A couple announcements. First off is that you have your next homework posted. It's homework number 7. It's on what we're discussing right now, which is failure of composite in principal material directions. So go ahead and take a look at that. After today's lecture, you should be able to get through all of them except maybe number 4. So look for that. That's going to be due next Monday, which is, I think, the 30th of October. So look for that. All right, I'm going to now flip it over to the writing pad so that we can go ahead and get on with the lecture. So here we go now. We should all see the writing pad on the screen, and I'm going to use this just like I use the whiteboard in class. One nice kind of thing about having this electronic version, though, is that I can bring in pictures from the PowerPoint, which is going to be especially helpful today. So just a review, last we left off, we were talking about principal and failure directions. So we were talking about, and what we've covered already is longitudinal tension, which, if you remember your picture, is just tension in the one direction. So unidirectional composite, something that looks a bit like this. And we got our fibers here running through sort of the height. These are our fiber direction. Longitudinal tension would be sort of pulling in this direction. We call this sigma 1, stress in the one direction. It was quite a complicated case. We saw that that was governed by strain to failure of the individual components, so the fiber and the matrix. And because the materials don't fail under the same strain, we get a lot of different crazy things that could happen. So don't want to belabor that too much, but that's one of the failure modes that we talked about. We also talked about transverse tension, which is tension in the two direction. So we got something that looks like this. Again, our silly model composite got all the fibers running in this direction. We call that the one direction. And transverse tension would be tension in the two direction. So we're loading across the fibers. We said that this particular failure mode is governed heavily by the failure strength of the matrix and the stress concentrations inside of that composite. So we said the failure strength in the two direction and tension is just going to be the failure strength of the matrix and tension normalized by the stress concentration factor. We label that as K sigma. And the stress concentration factor is dependent on things like the fiber volume fraction and the moduli of the matrix and the fibers themselves. So those are the two that we've covered. And those are 2 of the 5 that we're going to discuss. And so let's then move on and discuss the next topic, which is going to be longitudinal compression. And just like longitudinal tension, longitudinal compression is complicated, but not for the same reasons that longitudinal tension is complicated. So longitudinal compression, the picture that you want to have in your head, just because, I'm drawing all these pictures, might as well add this one as well. Here's your composite, got all the fibers running this way as per usual. Longitudinal compression is this general loading mode, where we now have a stress in the one direction but not in tension. Here we are in compression. And the reason why this mode is so complicated is because you get a lot of different failure types that can occur based on volume fraction of fibers. So we really have 3 main modes of failure. And I'm going to list them here. The first is fiber buckling, or what we call micro buckling. So I'll just say buckling of fibers. And within this buckling of fibers category, we kind of have 2 separate categories. And so maybe you label this as 1A and 1B. And we can have what's called out of phase fiber buckling and in phase fiber buckling. So could be out of phase. This happens at low VF. Or B, you could have in-phase buckling, and this happens at high VF. Okay, I'm going to bring in a picture here now from the slides that sort of shows what these buckling modes look like, and it kind of, I think, helps tell the case of this fiber buckling condition. So here's a nice picture, probably better than what I could draw, of in-phase and out-of-phase buckling. And I think you sort of now can sort of see what the buckling of the fibers might look like in these particular cases. You've probably seen buckling in your mechanics of materials classes, and so you definitely start to see those mechanisms here with the fibers inside of the composite. And so when you're starting to put compression on the composite, you're putting compression on the matrix, compression on the fibers as well. And because these fibers are long and slender, they can actually buckle inside of the matrix material itself, which is kind of unusual. If there's enough fibers, so if you have a very high volume fraction, you start to get this in-phase buckling where these fibers are all kind of like working together or buckling in the same way. And that's because when you have a lot of fibers, they sort of like communicate with each other about like, okay, bud, what are you doing? What are you doing? Okay, we got to sort of work together to all buckle in the same direction. Otherwise, none of us are going to be able to buckle. And the fibers eventually talk to themselves and work it out so that they all sort of buckle in the same way. And that really only happens when you have a lot of fibers. Otherwise, this individual fiber here, if you have a low volume fraction case, just doesn't really need to communicate with his closest neighbor to buckle. He just has the space to do it. So that is one way that composites might fail in longitudinal compression, this sort of like fiber buckling method. A second way is, and this is going to look a little bit strange when I write this, but one other way that they can fail is in transverse tension. And what do you mean? Transverse tension we talked about already when the loading was directly in transverse tension, the loading directly in two. So how, if you get longitudinal compression in one, like we have here, might you have failure in the two direction in tension? Well, the reason that is this is purely from Poisson effect. And what I mean by that is like if you have any material, think about aluminum or steel or whatever, it doesn't necessarily have to be a composite, and you put this into longitudinal compression, kind of like what we're talking about right now, sigma 1, what happens is you put this thing into compression, it's going to want to expand in the 2 and the 3 directions this way. So here we're going to write epsilon 2 from Poisson effect. Right? Because you're putting compression on it this way and it wants to, expand in the 2 direction. And so what happens is because that 2 direction in composites is so weak, so 2 direction in tension, very weak. This response, which is this Poisson response causing the composite to want to expand in the 2 direction, might in some cases be enough by itself to cause the composite to fail in the 2 direction in transverse tension, which is wild. You think about putting compression in the 1 direction and it fails by transverse tension in the 2 direction. Okay, so that's kind of an interesting phenomena, but definitely happens because composites are so weak in the 2 direction in tension. And the last type of failure that you might get is just a full macro scale shear failure. So this is macro scale shear. And I have a nice picture of this in the notes. I'll pull that one in here because better than what I could draw, especially this one. This one's like, man, this one's hard to draw. This is like a typical shear failure that you might see in like a metal. All right, like an aluminum. All the grains inside the material want to align sort of at a 45-degree angle with the load, and then they're going to start slipping against each other and sliding against each other. That's more or less what's happening here, is that, this usually happens at very high VF. We're talking like 70+% volume fraction. You put this thing into compression and it just, eventually the entire thing kind of shifts and sort of cracks in half along this sort of shear plane, this 45-degree sort of angle. So those are the three ways in which it can occur. So let's go ahead and look at the math associated with these three different methodologies, and we'll start with the microbuckling. Okay, like I said, there could be two different ways that this could happen. It could be in phase or it can be out of phase. And the math associated with those two are quite different because whether or not the fibers can communicate with each other side by side plays an important factor on how much load you can allow before buckling happens. Okay, so at low VF, we're talking 10-ish% or less. I'll say 15% or less. You'll get out of phase microbuckling. And again, what that picture looks like, I'll just bring this in here for reference. It'll look a bit like this. But pause the video if you want to sketch this. Haha, you like that. All right, so at low VF, 15% or less out of phase microbuckling. And in this case, I'll just put the equation of how the strength is predicted. And easier to just copy it from the notes because it's going to be cleaner. This equation here. It's 2 times the volume fraction multiplied by the square root of the elastic modulus of the matrix, elastic modulus of the fiber, volume fraction of the fiber, 3 times 1 minus VF, or what you might call VM, right? Volume fraction of the matrix. All right, so that's what we got going on here. Importantly, if there is a distinction here, you want to use E1F if there's a difference. So the modulus of the fiber in the one direction. If you have the choice, that's because we're talking about failure of the composite in the one direction. All right, so if you happen to have a transversely isotropic fiber, which carbon fiber is, Kevlar fibers are transversely isotropic, then you might have a modulus in the one direction that's different than a modulus in the two directions. So important in this particular case, if you're going to use the elastic modulus of the fiber, that you know which one. And so in this case, we're going to use the elastic modulus of the fiber in the one direction. So this is for out of phase microbuckling, right? So out of phase, OOP, microbuckle. And this is valid in the range of like 0 to 15% volume fraction fibers. And that's because, you know, you need a low enough volume fraction where the fibers are not really like communicating with each other or giving information about how they're particularly going to fail. Where does this come from? Well, this comes from a number of different places. It comes from theory on buckling in a situation where fibers are constrained by a lateral load. So if you think about sort of this condition where you're applying buckling this way, and then you're allowing for some restriction from the matrix, which is like a distributed load on either side. This is kind of how it's derived. The derivation is actually kind of long and kind of outside the scope of what we want to do in this class, but it's more or less coming from the theory of this, right? Where you've got a single fiber constrained by matrix where that matrix is not necessarily like super stiff, right? So the matrix might have modulus of 2 GPa, where the fiber might have a modulus more like 100 GPa, something like that. So it's coming from that theory. That's all I'll say about it. I think that's all that's really important here. So I'll just move on. So that's low volume fraction. You get this out of phase microbuckle. So let's talk about at higher volume fractions. And here I write in the notes greater than 10%, but let's say, you know, 10% or more. That's roughly it. Maybe 15 to like 50% would be a reasonable value here. This is going to be in phase. And again, just so you have that picture. it looks a bit like this. So here's your in-phase microbuckling. And now the fibers are close enough to each other here and here where you can no longer just assume that you're going to be restricted only by matrix on the left and the right-hand side, but now you're restricted by both matrix and some stiffness of the fibers next door. And it's getting to a point in that case then where you're almost going to be all failing together in at a certain time, because all these fibers have to sort of communicate with each other and say, hey, are you going to buckle? Are you going to buckle? Because we all kind of got to do this at the same time, right? It's like going at a green light in traffic. It's like, can we all just go at the same time? All these fibers are getting loaded, and they're like, are you going to buckle? Are you going to buckle? Man, this load's getting pretty heavy. Let's all just go. And then finally, they just all go. And because of that, they kind of buckle into an angle that is like this, like a 45 or roughly a 45. You get kind of like this angled situation there. And whenever you have these kind of like off angle loading situations, you want to be thinking about shear and shear effects. And so just because of the way that this works out, the strength of this happens to be highly correlated with the shear modulus of the matrix. Okay. And so correlates with shear modes of loading. And then the strength is going to be given by here, F1C is roughly equal to, this is the shear modulus of the matrix, GM over 1 minus VF, or what we would say VM. So that's pretty straight ahead equation. Shear modulus of the matrix divided by the volume fraction of the matrix. Again, a lot of empirical testing done to kind of get this correlation and understanding about like how the shear strength of the matrix is the one that's really influencing when all the fibers can sort of like buckle together. So that's the situation. That's what's going to happen. Now, I want to talk a little bit about this sort of the structure that happens in this in-phase microbuckling over here. And you sort of start to see all these fibers like taking on this pattern of sort of like this S shape. Okay. And this S shape is kind of like a precursor to a particular type of damage mode, which is seen like pretty commonly for composites that are failing in compression. And that's a kind of a phenomena called kink banding. So let's talk about kink banding for a second. So kink banding happens in composites that undergo this microbuckling phenomena. So it occurs, and it's a mechanism of failure in composites with microbuckling. And I'm going to bring in some actual real life pictures here, but I want to talk a little bit first about like a cartoony picture that I think tells the story. And it correlates well with the images that we've seen so far with this sort of microbuckling. So if you could imagine the in-phase buckling, which we talked about already up here when this thing is in compression, this is going to load until eventually these fibers just can't handle the shear stress on this anymore, right? And so those fibers are going to eventually rupture and break. And they're going to do so in a pattern that looks like this. They're going to take this S shape that they've got right now and eventually give out and eventually fracture. And they tend to fracture along these planes that sort of run at a 45-degree angle with the direction of loading. And this here, this sort of looks like a railroad track a little bit. It's called a kink band. Okay, and it's just what happens when the fibers kind of all give out and say, man, I just can't hold this compression anymore. I've got to fracture and sort of shift myself into a lower energy mode so I can relieve some of the compressive strain that's on this composite. So that's kind of the cartoony version of what this looks like. And then we actually have like in the notes, I pulled a picture of a real composite that's got this kind of failure mode to it. So this is the cross section of a composite that has actually failed with this concept where it was loaded in longitudinal compression. The fibers buckled in phase, and then eventually with increased loading, the composite just gave way and these fibers fractured. And so this thing is being loaded in this direction, right? And you see that like railroad track here now that has occurred. And this is called a kink band, where you've got to relieve some of the compressive strain on the composite. And the way to do that is to sort of cause this thing to kink and give you a little bit of like relief, more or less. So that's what's happening there. Kink banding, pretty cool thing. Happens without a phase microbuckling. Okay. So that is one way that composites can fail in longitudinal compression. So buckling of fibers, we've talked about that. We're done with that. Let's move on now and talk about this interesting case, this transverse tension case. And I talked about this a bit already, but if you're going to load something in compression in the one direction, it's going to expand in the two direction by Poisson effect, right? So remember, Poisson's ratio is like the transverse strain, which occurs over the longitudinal strain. It's the opposite of this, right? So this is the definition of Poisson's ratio. And so if you have a negative longitudinal compression, which is what we do when we apply sigma 1 in this like compressive methodology, then you're going to have a positive transverse strain. So this thing's going to get longer in the two direction when you compress it in the one direction, right? So how can that lead to failure? Well, there's some sort of math behind this, and I'll show you what that math is here now. So let's get into failure by transverse tension when loading in longitudinal compression. So transverse tensile failure under sigma 1 compression, right? So we're loading in sigma 1 compression. We're not actually applying any transverse tension in the two direction. We're not loading with stress in the two direction. It's just a result of the Poisson effect. All right. So there's a bit of math here, and we can look at the math. So investigate math of how this works. Poisson's ratio 1, 2. This is going to be, we sort of saw this already. How much do I compress or elongate in the two direction if I compress or elongate in the one direction? It's this ratio of how much strain exists in the transverse direction given some applied load in the longitudinal direction. Fine. So this is just the definition of Poisson's ratio. Now let's move on. Next step is to say, all right, we're going to fail if the strain in the two direction reaches some ultimate strain. So it reaches some ultimate value. Fine. No problem. So let's put that in here. And we can rearrange this a bit. And write that here, this is the strain to failure, and I'll put the negative sign, negative on the other side. In the two direction, ultimate. So this is the ultimate strain to failure in the two direction is going to be negative nu 1, 2 times epsilon 1. All right, no problem. We're just sort of rearranging this a little bit. All right, we'll say that we don't want to write this in terms of strain to failure in the two direction. We want to say that at failure, the stress in the one direction is F1C. All right, so we're going to let the strain in the one direction be negative F1C, right? Because we're putting compression on this, so we put a negative sign in front because we're adding a negative amount of stress. So it's the negative failure strength in the one direction and compression divided by the elastic modulus of this composite in the one direction. I think this is just simple Hooke's law. it tells you we're going to fail in the one direction at F1C. And if we want to determine what that is, we need the elastic modulus by Hooke's law to sort of bring this in. And so we can sort of keep moving on all this together. And this negative and this negative are going to cancel each other out when I make the substitution. So here, this is going to be something like nu 1, 2 times epsilon 1, which is F1C, now over the elastic modulus in the one direction. Okay, well, that's very nice. Ultimately, we want to solve for this F1C. That's what we're looking for. So we're going to rearrange for F1C. And so we'll say F1C. This is equal to the modulus in the one direction times the strain to failure in the two direction, this ultimate strain to failure in the two direction, divided by Poisson's ratio, 1, 2. We're going to introduce a new method for the strain to failure in the two direction, and this is called the Nielsen approximation. So introduce the Nielsen approximation. For epsilon 2 ultimate, which I do have in the notes, but this is an approximation based on stress concentration, strain concentration theory. And I'll just present it here with no additional comment. And that is that the strain to failure of the matrix in the ultimate sense depends on the volume fraction, to the 1/3. This is a purely empirical observation. So this was basically just done by testing in the lab. So empirical, meaning this is from experiments. It's not really derived from any theory. It's just derived from somebody did a lot of experiments, and then this happened to correlate very well with those experiments. So we can plug that in here now. Okay, so I will introduce this as 1 minus VF to the 1/3 times the strain to failure of the matrix. So this is strain to failure of the matrix. Right there. Strain to failure of the matrix. And, I'll write that here. Which, by Hooke's law, if you want to sort of figure this out, is going to be, the strength of the matrix in compression or tension divided by the elastic modulus in the matrix. That's one way to sort of figure that out. What's the ultimate strain to failure of the matrix in compression? Well, it's the failure strength of the matrix in compression divided by the elastic modulus. Okay, so that's fine. And then don't forget about your denominator over here. There's a new 1, 2. Last thing I want to say is that we have expressions for E1 and nu 1, 2. So those guys can be found using our rule of mixtures. So hopefully remember rule of mixtures from like the Halpin psi micromechanical models portions of the class. And so these guys can be found with rule of mixtures. And so finally, we can get to the expression for F1C, which is the failure strength if you're providing compression in the one direction that results from transverse tensile failure, which is really kind of unusual, is our rule of mixtures. So this is E1F BF plus EM BM. This is rule of mixtures for the elastic modulus in the one direction, multiplied by this Nielsen approximation, so 1 minus VF to the 1/3 times the strain to failure of the matrix in compression, so EMU, which we saw over here. So if you want to write it using that methodology, you can do that as well. And then this is all divided by the Poisson's ratio, nu 1, 2, which can also be found using rule of mixtures. So here this is going to be nu 1, 2, got to move this down a little bit, of the fiber, volume fraction, plus nu 1, 2 matrix, volume fraction of the matrix. And this is your prediction for the strength in the one direction in compression if this thing might fail in transverse tension from Poisson effect. Very, very wild stuff going on here. All right. So that is the second of two ways that your composite could fail if loaded in the one direction in compression. So all the way back up here now. We've talked about buckling of the fibers, how these guys fail, out of phase and in phase. We've talked about transverse tension now, presented the math on how that's going to fail. And now let's cap it off by talking about this last one here, which is this macro scale shear failure. So this guy here is like you have tons and tons of fibers packed into the material, and it all just kind of fails at one moment. So that's a little bit different than kink banding. Kink banding, you have sort of this slow progression where these things buckle a little bit, maybe in one location of the composite, and then eventually you get them to load a little bit more, a little bit more, and then they kind of break like that. Macro shear failure is similar, except you don't really see any pre-indication of failure before it goes. You don't get to see that fiber buckling at all. It's just all of a sudden very catastrophic failure of the composite. So let's talk about failure by shear. And I'll say in macro scale shear with sigma 1c loading. All right. I got to drill this into your head. This actually doesn't happen very often in practice ever. That's because usually you don't have high enough volume fractions for this to happen, but sometimes it does happen. So let's put the caveat here, only at very high VF. We're talking 70+% VF. Very, very high. All right. And it's just like a very densely packed forest of fibers that don't allow any motion for any of the individual fibers prior to this whole thing breaking. And this is what the failure looks like. Again, the notes are nice because I can pull in this picture here. But this is a bit like what it would look like right as it failed. So we've got, this sigma 1 in compression on this particular guy. Very, very high amounts of compressive loading until bang, this entire thing like shifts down against itself, and we're just like basically like we sliced it at a 45-degree angle, more or less. All right. That only happens at really high volume fractions. Very sudden, not a lot of like precursor to this happening. And catastrophic. All right. And I'll say this doesn't really happen very often. So not common. And that's mostly because you need really high volume fractions to have this happen. And most composites these days, if you're made out of woven fabric or what say you, it's going to be volume fractions in the 50 to 60% range, not really 70+%. All right. So how does this happen? Or what's the failure strength? Well, I'm just going to kind of cut to the chase, and there's some math in your notes. I don't want to go all that crazy on it. I just kind of want to cut to the chase. There's a bunch of math in the notes. It has to do with fiber buckling and some shear. Let's make some notes on it. Governed by shear of fibers matrix sort of all at once. And so when you think about what's going to be included in this failure criteria, it's going to be like the volume fraction of the fibers is going to play an influential role, and the shear properties of both the fiber and the matrix are going to play an influential role. And so there's some additional math about how to get to this in the notes. I don't think it's all that important that you understand the math totally and fully, but I'll just cut to the chase and sort of copy and paste it down here from the notes in the interest of time. And looks a bit like this. So here's the fiber, the failure of the composite in the one direction, and this is from macro shear failure. All right, so what are the items that you see here in this equation? Okay, obviously you see volume fraction. That's well understood. Here is matrix fraction. Remember 1 minus VF is the matrix fraction. It keeps VF in this equation because, you know, maybe you want to use VF as an independent variable in an equation. So, okay, but this is volume fraction of the matrix, fine. And then this here, this is shear moduli of matrix and fibers themselves. So you got this ratio here. And a lot of this information here is more or less coming from some rule of mixtures nonsense that gets played under this particular type of loading. But that's what happens. And the last and probably most important piece of information that you see here is this value, FFS. This is the failure strength of a single fiber in shear. Right. This is actually a very difficult value to obtain experimentally. And why is that? Let's say I wanted to determine what's the shear strength of a single fiber, and I need to design a test to do that. So think about the test that you would need to do. So what test might you do? Okay, well, I got a single fiber here. That's my one fiber. And I need to apply a shear load to it, meaning I need to apply a shear load. Remember what your shear loads look like. I need to apply shear to that thing. Like, someone designed me a fixture to put a single fiber into shear. How are you going to do that? It's like actually very, very hard to do that. And interestingly, one of the ways that the shear strength of single fibers is determined is by putting a composite into compression in the one direction and then backing out this value, which is kind of wild. And then it's like, well, what came first, the chicken or the egg? What do people understand better, F1C from shear fiber failure, or can people calculate shear fiber failure first and then get F1C? It's just like chicken and egg problem. But we see that, okay, this failure strength in the one direction and compression is very heavily dominated by the failure strength of the fiber in shear, and it's quite difficult to actually do an experiment to calculate what that failure strength of a single fiber might be in shear, but it is what it is. And this is the theory, and it requires knowledge of the shear properties, the shear strength of a single fiber, which is actually pretty hard to know and understand. So often you don't have this value. Might not have this. So if you're going to think about utilizing this shear failure theory, be sure that that's what you want to do. You should have some real solid reason for going after this possible theory. You should have a composite that you're looking at with your hands that you have seen fails in a way that looks like this. And then you're saying, okay, if I see this failure, now I'm going to this theory and I really got to dive in on, okay, this theory here, and maybe it's worth investigating what's the strength of a single fiber in shear in this case, because it's probably going to dominate your properties. So Practically speaking, this type of macro shear very rarely happens. And the reason why is because it only happens at super high volume fractions, again, like 70% plus. So you don't often have to think about this so much, but it is something you gotta at least think about a little bit. All right, so that's it. That's your longitudinal compression failure. I did put together a slide for you guys. I'll just pop it on the screen here really quick. Um, this is a slide in the notes. It puts all of that information together in one spot. So here's your summary for longitudinal compression. There's these three main types of mode: out of phase, microbuckling, in phase microbuckling, transverse tension with Poisson effect, and then this macro scale shear. Here's the information associated and how you might calculate all these particular things. On your homework, problem number 5, I'm going to ask you, what is the failure strength of a particular type of composite across a wide spectrum of volume fractions according to these theories? You're going to graph all these lines on the same graph and say, all right, if the volume fraction is 10%, it's going to fail at this value. If the volume fraction is 30%, it's this value, and so on and so on and so on. Okay, so that's longitudinal compression. We've now done 3 out of the 5 failure modes. We've done longitudinal and transverse tension. Those are done. We've done longitudinal compression. That's done. And we have 2 more to go. And the 2 that we have left are transverse compression and shear failure. All right. Transverse compression is really easy. We're at 1:30, so I got about 8 minutes. Transverse compression, this is what we'll do next. And it's easy. It's very similar to transverse tension. And remember transverse tension, I'll go all the way back to the very beginning of the lecture. Transverse tension is this guy here, where we're loading across the composite in the 2 direction in tension. Very, very weak, dominated by the strength of the matrix, which is generally very low, and then being amplified by stress concentration factor K sigma. Well, I mean, transverse compression is more or less the same thing. You're loading now not in tension across the fibers, but in compression across the fibers. It's still bad. Not as bad as transverse tension, but still bad. All right, so let's just do this one really quick, and then we'll call this lecture here. All right, so transverse compression. Let's get this one out of the way here really quick. So picture in your head. I'll do it over here. Here's your composite, all your fibers going in this general direction. And we're going to put compression now in the 2 direction. So this mode again, dominated by stress concentrations, right? And it's going to look very similar to transverse tension. I'm just going to write it because there's nothing else really to say. It's the failure strength in the 2 direction in compression is the failure strength of the matrix in compression divided by the stress concentration factor, K sigma. That's it. Done. It's very similar to transverse tension. The only difference is instead of using the failure strength of the matrix in tension, you're using the failure strength of the matrix in compression. That's it. There's a picture in the notes. I'm going to bring that in because it's nice to see. And this is the picture you should sort of have in your head of what a composite's going to look like if you're loading in the 2 direction in compression and how it's going to fail. You start to see sort of this kind of shearing effect again, where it's going to like slide against each other. But again, it's because like stresses are concentrated around these circular inclusions, and eventually it comes free and just slides with what looks like sort of a shear failure, but it's really just from concentrations of stress around the fibers that cause the matrix to fail in that region. Remember what K sigma is. Now this is a stress concentration factor. I will just pull it in here really quick. Looks a bit like that. It uses the properties of the matrix and properties of the fiber in the two direction. So there's your stress concentration factor. Just to be clear, this square root ends here. I think I've seen that error from students before, is that this is kind of its own unit. So make sure that you're not including like this bit in the square root over here, okay? All right, that's transverse compression failure. I guess there's one last thing to do, and it's also quite quick, so we'll just go for it. And that's the failure in plane shear. This one is also dominated by stress concentration factors. The picture you want to have in your head, remember what in-plane shear is. And so what we're looking for here is what we call F6, which, you know, is like F12, which you might think of as like tau 1,2 ultimate. Okay, so if you have your typical coordinate system here, this is like 1, 2, 3. Well, let's do it a little bit different. Let's sort of change our coordinate system just a little. This will be 1, 2, and then 3 coming out this way. Just so I can make the picture a little bit cleaner, is that the loading mode that you want to think about is like this sort of loading mode. This will be like a tau 1,2, like a shear 1,2. So you're kind of like pinching this thing and sort of trying to turn it into a rhombus, where this is kind of like your fibers running inside of this piece. So what's the failure of this guy going to look like? Well, this is what the shear is going to look like kind of in the plane, right? So this is, again, applying like a tau 6, or shear stress sort of in the plane. So you see like, this would be like the 1, 2 direction, something like that, right? And there's a lot of importance in this case about the interface between the fiber and the matrix. And that's because now the fiber is trying to slip or shear along that interface between it and the matrix. Okay, so interface is important here. But if you assume a perfect bond, then again, it's governed by shear properties of the matrix and stress concentration factors. So in this case, it's going to look a lot like your transverse compression and transverse tension. And it's that the failure strength in the in-plane shear condition is the failure strength of the matrix in shear divided by the shear stress concentration factor. So here this is matrix shear strength. And this K sigma is shear stress concentration factor. And that is given by the following. Looks very similar to the stress concentration factor for transverse tension and transverse compression. And it looks a bit like this. So you have it. Pause the video if you want to copy it down. And so when this thing ultimately does fail, like if you do have this sort of shearing going on for this particular piece, then this thing is going to ultimately fail between the fiber and the matrix. Something that looks like that. Usually within the matrix, it's going to fail because the matrix was going to have a low shear strength. And failure usually in the matrix, right? So shear failure of matrix. And that's all she wrote. 138, 50 minutes exactly. So those are the 5 ways that you might fail in a composite. So we talked about longitudinal tension, longitudinal compression, transverse tension, transverse compression, and now the last one here is in plane shear failure, this F6. But now we got them all. These are all if you're only loading with that particular type of loading. Only if loading in the one direction in compression. Only if loading in the 2 direction in tension, or whatever the case may be. Okay. In reality, composites are loaded with many different types of load. You could have a combination of many of these types, and they don't necessarily have to be in a principal direction. It could be a stress and some random orientation. So let's say you've got fibers that are going here, and what happens if your loading is, something like this? We call it sigma x off axis. How can I predict when that composite is going to fail? That's what we're going to talk about in the next lecture, is how do we deal with loadings when they're not all perfectly in the direction of our principal material coordinates, which they often are not. So I'm going to bring it back here to the main screen, stop sharing, and say, you're armed now to do homework 7. You should be able to do all 5 problems now. Most of them are pretty quick calculations. I'd say number 2, 3, and 4, pretty quick calculations. You should be able to get through those pretty quickly. And number 5 will take you a little time with the graph, but that's that. I'll be back on Friday after my jury duty is hopefully done. Hopefully I don't get roped into some like multi-week long, bank robbery case or something. I don't know. But until I see you again, peace.